Good day everyone, my name is Nazmi Sofian bin Sohaimi. I'm from the Faculty of Computing and Informatics, and today I will be presenting the topic Leveraging Emotion Prediction Artificial Intelligence with Consumer Accessible EEG Headsets. So what is an emotion classification? It is the collection of a continuous brainwave signal and prediction of the emotional state of a person. The brainwave signals are recorded using an EEG headset that is non-intrusive and safe. The brainwave signals are then transformed using fast Fourier transform into specific bands, and this presents a novelty for stimulus application in affective computing. So these are the 5 potential applications that we're looking into, which are video gaming, healthcare, education, military, and entertainment. The studies reported that users VR with multi-sensor setup are Fan et al., which uses driving simulation, Hidaka uses the arousing VR scenes, and the multi-sensor listings consist of EEG, skin conductance, body temperature, breathing rate, and eye tracking. There are also other studies which uses purely EEG. Horvath uses NAPS, which is a realistic picture to stimulate emotional responses, and Guo et al., which uses the VR roller coaster to measure fear. Both of these studies measure the changes in energy ratio of independent waves. So the gaps in the work are, there are very few studies using EEG and VR, no emotion studies using EEG exclusively in VR. The applications are limited due to the EEG hardware restrictions, cost, and complexity. And the complexity of a 4-class emotion classification from general standpoint made it difficult to integrate for general applications. The study objectives here are to demonstrate using a low-cost wearable EEG headset for deployments in affective computing, to demonstrate the applications of the device by performing using 4-class emotion classification, and last but not least, to demonstrate the performances achieved from the classification model for public applications. So this model, which is a 2-dimensional space model known as arousal valence space, is used as a guideline to select the emotional representation of each quadrant. And next, we use the neural network, which is a supervised neural network with many hidden layers. This is used for classification or regression analysis, and this has shown great capabilities of classifying emotions from music and EEG signals. This is the research methodology. So we have the first step is the brainwave collection using 4-channel Muse interaction on these locations, decomposed with FFT to obtain the 5 bands and inertial sensing data, and this is sampled from 31 participants. The stimulus for the participants are using a 360 YouTube video, which consists of 20 seconds each video, and in each quadrant there are 80 seconds, which means there are 4 clips per quadrant. And it is arranged from Q4, Q2, Q1, and Q3 stimulation responses. And in each transition of the quadrants, there is a 10-second rest. The data cleanup is the third step. And last but not least, we have the training and performance evaluation of the classifier model. So we separate the data with 90% training frame and 10% testing and validation. The classifiers used are random forest, gradient boosting machine, and naive Bayes. So here are the results that we did from the 3 classifiers. We can see that distributed random forest achieved the highest classification accuracy for 4-class at 82.49% on both with the inertial sensing data and without the inertial sensing data. As you can see from the other results, using the inertial sensing data actually improves the accuracy compared without the inertial sensing data. So here we developed a live prediction system for emotion predictions, building a system using Anaconda with Scikit library for prediction model. We use Flask to host the local server and the Muse LSL library for communication between the EEG headset device and the local server. So this is the screenshot of the live prediction modeling system. Here is the live prediction right now that is running in the network system. So as you can see here, we have the values. The value represents the emotional state of the person, and this is the predicted emotions, which represent the results. These are the sample codes that are running behind the background for collection of EEG signals coming into the device and displaying the local server results. So the possible solutions now that was developed from the system shown just then is that for video gaming, it can be used for adaptive difficulty based on the player's mental state. The healthcare system can assess the patient's mental state much quicker and easier. For education, we can assess the student's attentiveness towards the classroom. For military, we can train the army to be able to adapt for different surrounding training. And last but not least, for entertainment system, the system can actually present some choices of video contents based on the current mood of the users themselves. So for our intellectual property here, our emotion classification model is our intellectual property. So as a conclusion, we use the distributed random forest classifier, and the performance achieved from the classification accuracy is 82.49%, and this is on a 4-class emotion classification. The prediction modeling system can be adopted for various applications. The cost of the hardware deployment used in this system is relatively cheap and easy to set up. And most importantly, the model can be integrated with any system because it is open source. These are the references that I have used. And this is my published papers for your reference. And we have come to the end of my slide. Thank you very much for listening in.